If you haven't already, sorry, I didn't anticipate this, but if you have drawn any of your graphs, your axes across the page, can I recommend against you doing that? The whole point of this exercise is, I mean, you know what these look like, but I want to make some comparisons against displacement, velocity, acceleration across time. It's going to be super useful to be able to say, look, here is one instance in time, and I can tell you about all three of these quantities just by looking at what they're equal to vertically. Okay, so if you haven't already, do them down the page. I'll give you another minute or so. Now, it will help you to have a ruler with you as we go through this, okay? Because as I said, the point is not, can you graph these? That's kind of a foregone conclusion. I assume you can graph these. Maybe that was a wrong assumption to make. The real thing that I'm looking for is, can we draw some conclusions about motion by looking at these graphs? And a ruler will help you compare displacement, velocity, and acceleration all at the same time, assuming you have a reasonably consistent time axis, okay? So, for starters, let's just think about displacement, okay? What's this thing doing? It's going up, and then down, and then up, and then down, or right, and then left, and then right, and then left. We could have changed all of that, obviously, if we had changed the phase, right? But that's what it's doing, and that's fairly simple. We get that, okay? Good. Let's move down and see if we can draw some conclusions and see what's going on, okay? For instance, when you've got, where's my, that's weird. Okay, doesn't matter. When you've got something like this, on this graph, we call that a stationary point. What does that correspond to? Well, it corresponds to the fact that your velocity is 0. Of course it does, right? I mean, if we were thinking about this in y and x and dy and dx terms, the way you find a stationary point is by saying dy and dx equals 0. But instead, what I'm saying here is, look, when I've stopped moving, okay, when the displacement is not changing, what that means is that, oh, there's another one, okay? That means velocity is 0. Cool. That makes sense. What else can we see? Tell me, where is the particle moving fastest? The particle is moving fastest at these extremities, right? Because what does this represent? For instance, this moment in time, right? T equals 0. This means that I am moving in which direction? Let's keep it in up down because that will be less confusing. Which direction am I moving in? This is the velocity graph. This is the velocity graph, and this is displacement. So when I look at velocity and I see that velocity is, well, for this graph, velocity is 1. It's positive 1. So which direction am I going in? I'm going up. Of course I'm going up. Look, see, there I am. There he goes. Okay? So does that make sense? Now, as it goes down here, what's going on? Velocity is going from 1 to 0. It's at 0 now. What does that correspond to? I'm slowing down. I'm still going in that direction. I haven't turned around yet, but I'm slowing down until eventually I reach a stop. Cool. That makes sense. Alright, but what happens? It continues. It turns around. This is a turning point, which corresponds to a change in sign for the velocity, right? Like it literally turns around. Okay. So that's why it becomes negative over here. And how would you describe the speed as I go from this point to, well, what's that? That's pi on 2, isn't it? Pi on 2 to pi. What's happening to the speed? The speed is increasing. You gotta be careful about how you talk about this. Would you say the velocity is decreasing? You probably could, but it's a bit tricky. The word decreasing is kind of like the word decelerating. Right? The way we use it, we tend to mean it's getting smaller. Well, it's getting more negative. That's a better way to say it. It's less ambiguous, okay? So I am moving faster and faster in the downward direction till I get to here, right? This is the fastest point at which I'm moving downward, and it corresponds to this point. So what does that mean? At these points here, 1, 2, 3, 4, 5. What do you say about the velocity at those points? That's where you have the greatest velocity, right? Which corresponds to, of course, the displacement graph being steepest. Have we squeezed everything out of the velocity graph that's interesting? Is there anything else that you notice? Looks okay to me. Well, let's move on to acceleration. What do we see from this guy? Okay. Well, again, let's start at the origin. Here I am, time 0. Okay. What acceleration is the particle, object, whatever? What acceleration is it experiencing at time 0? It's not experiencing any acceleration. But the second I move off that, the moment I move off, right, after time equals 0, what is the first acceleration the particle experiences? It's acceleration in the downward direction. Does that make sense? Yeah, it does. I am moving up, but I'm moving up at a slower rate because something's pushing me down this way. It's pushing me down so hard, eventually I stop. Right? Now, have a look at that point where I stop. What time is that? It has a value. What time? It's pi on 2. Okay? So at that point, I'm at the extremity of motion. At that same point, I have velocity 0. What's my acceleration at that point? At that time, I should say. That's this point here. So what would you say about the acceleration? This is the strongest the acceleration gets, isn't it? That's the most negative it gets, right? So the further away I am from my center of motion, the harder I'm being pushed back to the center of motion, which of course is why he always comes back, right? You can see if I go along to, what's his time? 3 pi on 2, right? When I go to 3 pi on 2, in the same way, my velocity is 0, and here, 3 pi on 2. Again, the acceleration is at its strongest in the other direction, upwards. I'm being pushed back toward the center of motion, okay? In fact, I'm always being pushed toward the center of motion. Can you see that? Have a look, watch with me, right? Because this graph is sine t, and this is negative sine t, right? If this guy is in the positive direction, I'm being pushed in the negative direction. Can you see that? See that correspond? If I'm in the negative direction, I'm being pushed in the positive direction. Of course he has to be. Because if he was in the positive direction and he was being pushed in the positive direction, he'd never come back, he'd just go whee, and off he goes. Right? See you later, guys. Not simple harmonic motion. Okay? Now, get into acceleration. Acceleration is really where all of the interesting stuff happens. Okay? Because of what we've been saying, if you're positive somewhere, right, then your acceleration is negative and vice versa. But not only that, the more positive your displacement is, the more negative your acceleration is, right? So in fact, I could say, rather than saying acceleration is a function of time, acceleration as a function of time, clearly I should be able to say, I could reword acceleration as a function of displacement. Namely, depending on where you are being accelerated in a certain way, namely the other way, right? The more positive you are, the more negative you're being accelerated. The more negative you are, the more positively you're accelerated. Now, look at this. We just reasoned through it by looking at what this all means. But you already saw it, I bet, when we developed these equations by differentiating, right? Of course you can see what x double dot is in terms of x. Because look, there's x. Well, I should say, there's x, right? Let me rewrite it for you. Come back to your time equations, right? If I put that n squared out the front, maybe I should take that negative as well. What I'm left with is a sine nt plus alpha. That's x. So I should be able to write this. Does that make sense? What's this saying? The further you are in a positive direction, well, your acceleration will be negative that. You'll be directly proportional. That's what this n is, just a constant, remember? Okay. Now, just be careful. I know we wrote it in the same spot because that's, you can see the progression, right? But this last line that I've just written, this guy, he's not a time equation anymore, right? We have a name for this. We introduced it under exponential growth and decay. It's an equation that relates a function to one of its derivatives, which we get by differentiation, right? Do you remember what it's called? It's called a differential equation. This is not a time equation. Because look, there's no time in there, right? This doesn't care when it's happening. All it cares about is where it's happening. So this is the differential equation. This is the differential equation for simple harmonic motion. Okay? Are there any questions at this point? How's your brain doing? Is it okay? Do I need to play the Doctor Who theme again to get you? Okay. Now, I will finish off before I get you to go at these questions by saying one last thing. Okay? We looked at these equations. We said, okay, it's got to be sine, cos, right? Can you see, by the way, I could just as easily have started with a cos nt plus alpha. Watch what happens. X equals a cos nt plus alpha. Tell me, what's x dot? Negative a sine t plus alpha. Yeah? What's x double dot? Negative a, another n, cos. Look, x double dot is still minus n squared x. Can you see it? Like it's still there, right? You will notice there's a different relationship between x and x dot here as there is here. I introduced the negative here, right? Which is why when you get differential equations for simple harmonic motion, they sort of conveniently leave out x dot. The real relationship is between not displacement and velocity, but displacement and acceleration. That's where the real relationship is. So I could just as easily have started from cos, then from sine. Why would you do that, by the way? Why would you choose this as your equation rather than that as your equation? Why might you favor one over the other? The difference between these, cos and sine, is just phase. That's the only difference, right? So really you would want this if you don't want to start at the center of motion. If you want to start, you know what cos looks like, right? If you want to start at an extremity of motion, you'll choose cos.